lecture. Since we don't have too many people, don't hesitate to ask questions so that we can have an entertaining and interesting lecture. Thank you, Shihan.
Thank you, Professor. Yeah, I'm Shihan. Very happy to be here to give a lecture about AI for robotics. Professor Edie told me it's like you should talk about something about AI for robotics. I know that's a way too big topic for me. I would just kind of butcher it. So today I'll probably just narrow down to the topics related to the general content of this class. We're going to focus on the Bayes filter and a little bit more. And a little bit background about myself. I'm currently a final year PhD student in the haptics, robotics, and the virtual interaction labs. Our lab focuses on all the aspects of the sense of touch, including how to present, how to display the touch sensations to the end users in the virtual reality, and how to create the tactile sensing in the robot applications for the robot to realize the actual manipulation tasks. And we are under the Department of Computer Science. And here is the general information about robotics at USC. We have, maybe you have noticed before, it's right. We have a Robotics and Autonomous Systems Center with a web page here, web page link. You can check it out more content about this center. And this is a center covering all aspects of the robotics. It's cross multiple departments under the Viterbi School. We have all different kind of interesting research about robotics. And more interestingly, we're going to move to the new computer science building this fall. For the most of the labs, are going to move to this new building. So it's a great time to look for some robotics research if you're interested. We have the new building, and we also recruited multiple robotics faculties in the past couple of years. So new building, new people, and waiting for the new research as well. So we're going to start with something relaxing, and just to ask the big question: what is a robot? So when you talk about a robot, what's the first thing come to your mind? It's like usually when you're trying to use a robot, you're trying to use a machine that to do something for you that's dangerous or dull or even or repetitive for the humans, so that you can spend more time for the thing you're really interested about. But usually it doesn't really work out in the way you want. So here are more videos, just the videos of failure with a more serious humanoid robots, which is a very challenging problem in robotics, considering the whole body coordination in the contact-rich environments. A few years ago, there is a DARPA Grand Challenge is asking the researchers to create the humanoid robots that can do the human-like tasks, something like going up a stairs and or get out of a car, or doing some simple task like to rotate a valve, something like that. You can see it's like any errors in the perception and the action will cause the disaster in the most of the cases. So what we really think about is a robot. Here is some good or successful examples that the robot are executing some daily activities. First, on the right side, there is the robot gripper, a robot manipulator, is trying to open a beer. As we know, it's like the robot open the beer is always the best robot. In this process, usually, sometimes only vision is not sufficient because when you're trying to open the cap of the beer, you need the precise force feedback as well to tell the robots, to inform the robots which state it really is, and then the robot can execute the further actions. And on the right side, this is a more challenging scenario the robots are dealing with deformable objects. The hard part of the deformable object is like it's very hard to describe the current object state. Imagine that the bottle of a beer is just a bottle of the beer. You can describe it as probably first thing you can think about is a pose, the 60 object pose, X, Y, Z, and roll your pitch. Those the 60 object pose is definitely one thing you can describe the object. And also, if you have further, if you have other more advanced representations of the object, including something like the center of the mass, or material properties, or even the internal structure, or like the internal structure, including how much liquid are in the bottle. You can create a list of the object state you are trying to track for a beer, right? For a bottle of beer. But for the deformable object, for a simple class, it's very hard to describe the current state of the class, right? If you think about that, first of all, you don't usually in the computer graphics you use the mesh, use the object mesh to create the shape and the current state of the class of the deformable object. But those mesh is, first of all, the dimension is super high, and the second is usually those mesh are highly occluded by other meshes, by other points. So it's very hard to simply create a unified way to describe those deformable objects. But for the robots, for humans, we may kind of using the empirical experience to just to pick up and fold a class. But for the robot, it needs the explicit description of the object states before it can execute any further actions. And these days, especially in last year, coming with the large language models, robotics researchers are also trying to catch up this trend. So there are a huge amount of research about robotics combining with large language models, and at the same time, people are also doing the scalable learning from demonstrations from the data collected from the kind of like cloud source data collection process across multiple universities. So for the robotics with language model, large language models, or robotics with visual language models, people are trying to combining the ability of the reasoning through those large language models with the robot action directly, kind of creating an end-to-end reasoning through the image and through the language to the action output for the robot. So here is kind of like example. It's like giving the command that place the apple on the table with I believe this is with the championship, the NBA championship of the last year. So then the robots can directly do the actions to place the apple on the logo of the Denver Nuggets, something like that. Usually, traditionally, this process is separated into the multiple stages, including the object state estimation and the motion planning and the reasoning, and then to generate the final action output. And nowadays, because of the ability of the large language models, people are believing that all these intermediate steps can be replaced by the black box of the large language models to directly generate action output. And on the right side is a learning from demonstration. Learning from demonstration is actually a pretty old concept. Could track it back to 60s or 70s, last century. So the key idea is trying to, because some actions or some skills of the robot is really hard to be defined or programmed by humans. So the better way to describe it is just to show the action or to show the skills to the robot directly. And the robot learn from those demonstrated paths or demonstrated trajectory to generalize to the similar, hopefully generalized to some similar tasks.
Excuse me, Professor. Could you clip the microphone a little bit closer or higher up on your shirt?
Oh, yeah, sure.
Okay, thank you.
Hello? What about now? Is it better?
Thank you, that's good.
Okay. Yeah. So that's about the robotics with learning from demonstration. And these days, the process of learning from the demonstrated trajectory to the new trajectory with new scenarios, in this process, usually, traditionally, there are simply behavior cloning, which is simply just a supervised learning network, trying to map the observation of the scenario and to the action, to the robot action. And these days, people are actually doing more generative models, like using the power of the diffusion models and trying to create more diverse trajectories given the demonstrated trajectories. And in that ways, which we can prevent the robot kind of stuck in a specific scenario and just doing the local minima because of the optimization process, just stuck in kind of a specific action in a specific scenario. So the robot kind of stuck in that local minima and cannot jump out to create more diverse actions and skills. So there's a huge debate about robotics these days because people are kind of believing the computer vision and the natural language are kind of has been addressed or has somehow be solved because of the power of the large language, because of the power of the huge data set and also the large language models these days. So is robots just, people are thinking, why robot hasn't been solved yet? Isn't robot just a share of the computer vision and the natural language? Is it really true? Some people believe and some people don't. And if the robot is just a share of the CV and the NLP, will robotics be solved by the methods applied in the CV and NLP? And also, there's a huge debate about should we focus on the development of the generalist robot or the specialist robot? Generalist robot is you have specific form factor. You have a robot with specific form factor, which can actually do a set of tasks quite decently, or you have a specialized robot, which is an expert on a specific task. What kind of robot should we go for in the future, and which one is more promising in terms of the technology difficulties? And also, should we, obviously these days, the data-driven, the learning-based method is much more welcomed. But because of the robot, to scale up the robot data collection is so hard, is so difficult in terms of the data collection nature. Should we also look into the physics-based methods in some way as well? This is also something we should probably look at. And lastly is just curious about your thoughts on the future of the robotics, because most of the best suggestions or thoughts are from the people kind of don't work on robotics too much, because they are not kind of constrained by the mind of the robotics yet. So usually the best suggestions comes out of those people. Quickly, I want to do an experiment. If you have a pen, let's just say if you have a pen in your hand, or even if you have a longer pen, that's better. So just place the pen on your two fingers. If you have a pen, let's just do a kind of a little bit DIY by yourself. Let's say what's really the robotics is. I have a chalk here. If you place the chalk on your two fingers, and the one is on the edge of the pen, and the one is kind of close to the center of the mass or a little bit shifted from the center of the mass. If you move your finger, one finger towards another finger, so what do you expect to happen? It's going to pop over? Yeah. What else? Other people also think so? You can do that by yourself. Move your one finger closer to another finger. Do you think the pen is going to fall off your fingers? No, right? Why it's not? Can you explain it by the natural language? Probably you even ask you to Google that right now. Probably it takes 5 minutes to find a paragraph to explain this scenario. But that's just the physics. That's the robots will probably handle in the reality. Because once you start with this test with a stable condition, that means the center of the mass of your chalk is always between your two fingers because the initial condition is stable. So if the initial station is not stable, if the center of the mass is falling out of your two fingers, and then the initial state, initially the pen is going to fall down. But once your initial condition is stable, and then no matter how you move your two fingers, the center of the mass is always going to stay between your two fingers. The pen is never going to fall down if the initial station is stable. So that's a very intuitive physics phenomena that we are experiencing in the reality, but it's somehow very hard to be explained, or kind of to be described, explicitly described by natural language or something, or even by the computer vision. That's, in my mind, in my opinion, that's the hardest part for the robotics. You have to deal with the unexpected contact, unexpected dynamics, and the complex physics during the interaction with the environment. And lots of these interactions and lots of these scenarios are hard to be described by natural language. And if you think about these scenarios, like natural language and the CV is the two tools to describe the dimensions of this world. But this world has some other dimensions that is hard to be described by those two tools. So we probably need some other representations of this world that could be maximally utilized by the robots. So here is a kind of boring definition about a robot. What is a robot? Robot, this is a quote from some famous paper or famous book I tracked from Google, which I think most people agree with. Robot is just an autonomous system which exists in the physical world that can sense its environment and acts in it to achieve some goals. And all those, the red words here, I think they are clear. The only one, but the autonomous may have some different definitions in different cultures and languages. But the core part is like we want the robot to make the decision to reason over the scenarios by itself. In this lecture, we're going to focus on some aspects of the robotics. We focus on the sensing and the estimation, and we're going to see how can we use the probability theory to kind of formulate this problem and also create a neat solution to create a computationally efficient and also practical solutions for the actual problems. So most of the content of this talk, of this lecture, is from the probabilistic robotics. This book came out about like 20 years ago. The core idea about this area is to represent the uncertainty using the calculus of probability theory. And for the two aspects that we're going to talk about here, the perception, we're going to regard it as a state estimation, and for the action, we're going to regard that as a utility optimization. Those are all came out the probability theory. So why do we formulate these problems? Why do we formulate the sensing and the estimation as a probability problem? Because uncertainty in the robotics is just inherent and fundamental. The uncertainty arises from four major factors. Definitely, generally it varies from much more other factors, but the four major factors here is first is about environment. The environment is stochastic and unpredictable. So this is quite obvious. When you're walking around in these classrooms, the environment is changing at every single moment. And the robot's action are also stochastic. If you look at the odometry data of the robot, when you're trying to turn the robot with 90 degrees, if you give the command of like turn left with 90 degrees, the robot will never get the exactly 90 degrees because of many factors, because of the manufacturing error, also because of the error in the error of the encoder, decoder of the motor. All of those will create an action close to the 90 degree, but never gets exactly on 90 degree. Also, the sensors are also limited and noisy. If you have a sonar sensor, and you're trying to detect the distance between your robot to the obstacles in front of you, in this process, you expect it will return the actual value between the robot and the obstacle, but actually, if there is a bump on the floor, and then this bump is probably going to reflect the signals much earlier, and give you the much shorter distance. And all of those factors are kind of unpredictable. And in the end, the models are inaccurate and incomplete. Even just for a simple 2D mobile or 1D mobile robot, the model we create for such robots are usually quite limited as well. So that's about all the uncertainties get involved in the robot. So the advantage and the pitfalls of using probability to describe all those, like all kind of get involved, consider those uncertainties, is it can accommodate. It's kind of like the advantages are all focusing on the uncertainties, the four major factors we talked about here. We can accommodate the inaccurate model, sensors, and of course also the actions as well. And the one thing is, like, compared to the learning-based methods, because of the probability theory, the mathematical background behind it, it's more robust in the real-world applications. And it is best to know approach to many hard robotics problems. And if you want to work in robotics, that's definitely the probability theory is definitely something you should be familiar with. But for the other side, could be quite computationally demanding. And also, the assumption here we are making is actually not that accurate. We have a false assumption that the real world, in some cases, doesn't really fall into the scope of the probability theory. And in the most of the case, it is a approximation instead of the optimal solution. All right, and we're going to jump into something that you're probably very familiar with. I believe this is the probability theory. The basis of the probability theory has been covered by this class in the session 19. So if you are confused about what I'm talking about next, you could also track back the lectures 19, which we are pretty much covered a similar basis, a mathematical basis in probability theory. So there are three axioms of probability theory. The first one, obviously, every probability falls between the 0 and the 1. And also, the true is 1 false is 0. And the third one is probably the most useful one. It's about the joint probability between the A and B, which it could be represented in a plot like this. And if we utilized the axiom 3, we can actually extend it a little bit more and into some more useful theories, useful definitions. which we'll cover in a bit if we use that. And in the probability theory, the minimum element is the random variables, and we divided this as discrete and continuous random variables. In the robotics, we're going to use mostly in the examples covered in this class, mostly use the discrete random variables. We describe the robot state. We describe the robot states and actions and the sensing measurement as a discrete, as a separate variables. And a quick example here for the discrete random variables, we call this the probability mass functions for the actual probability value. And here is the continuous random variables, which is pretty much very similar to the discrete ones, except the probability value of each variable, we call it kind of probability density function, just some terminology differences. And the probability value in a specific range is actually not a summation, but an integral with the variable itself. So here is a couple of quite important theories, important definitions: joint and conditional probability. So joint probability is defined as the P of X and Y, which means it is the probability of two events are happening at the same time. But if X, Y are actually independent, this joint probability could be represented a multiplication between those two events. And for the conditional probability is defined as a probability of X given Y is the probability of X is happening given the Y is actually happening. So there is a subtle difference between the joint and the conditional probability. And for the conditional probability, it's actually defined as the joint probability divided by the probability of the given event Y here. And if the X and the Y are independent, the joint probability is just the probability of the event itself. So the last equation here is actually could be derived by the definition of the joint probability. Hopefully this is very, very clear for most of you. And the law of the total probability, which is also quite important and will be used multiple times in this lecture later. The total probability, obviously, if you just count all the events, count all the possible occurrence of your event, and then the probability eventually is going to be 1. The difference in the discrete case is the summation, and in continuous, you just do an integral. And another two things here is the marginalization and the conditioning. For the marginalization, the probability of one event could be if you introduce another event which is Y, and you do the summation over the joint. You do the summation over this joint probability based on the new introduced event Y, and then also gives you the probability of the current event. The conditioning is slightly different. We are using the conditioning probability instead of the joint probability, but the same thing is like we're introducing a new event Y here, and then when you calculate when you multiply the conditioning probability X given Y with the new introduced probability with the probability of the new introduced event, and then it's also going to give you the probability of the current event X, Px. All right, hope this kind of leaves some impression in your mind, which is the total probability. And there are two important sub-concepts under total probability is marginalization and conditioning, which is utilizing the joint probability and the conditional probability to infer the probability of the current event. All right, and a quick history about the Bayes rule or the Bayes or the Bayes-based probability theory is created back to the 18th centuries by the mathematicians, including Klarman. They first introduced the probability inductively and established all the mathematical basis behind. So utilizing the definition, we provide for the joint probability Pxy, and then you can actually rewrite the joint probability Pxy in those two different variants. Depends on the position of how you put x and y, right? And those are equivalent. And then based on the variants of those, based on the two variants of the joint probability Pxy, you can derive the probability of conditioning probability x given y in the following format. And this is the famous Bayes formulation. And if you're trying to interpret this Bayes formula, the numerator is actually the prior likelihood, and the denominator is evidence. So you can understand it as the x given y, the probability of x given y is something relies on the prior knowledge of your system and the evidence you can collect it at the current moment. Another thing is the normalization. Normalization basically simplifies the Bayes formula a little bit because, as we talked about, the denominator here is evidence, and usually the evidence could be represented using the total probability introducing a new event. And this introduced a new event could actually be any new event. So if we know a specific event, we know the probability of that event in your system, you can just grab it and use it. So that could help us to create a normalization factor to simplify the expression here. I'm going to skip the algorithms here, but basically it's about any new introduced event x could be used to calculate the total probability of the rational event. So, and this new event could be irrelevant to the event we actually care about in the original x given y. And here is the conditioning about the Bayes formula. What if we have a new event introduced into our formula? In this case, we have a new event z that is not considered in the rational formula. It's not considered in the original Bayes formula. So what we can do is taking the x given y as a whole, as a whole unit, and again apply the total probability to consider the new introduced event z here. And also, similarly, if we're trying to create a variant of the Bayes rule with background knowledge, here we define the background knowledge as z as well. And then we can simply think about the rational x given y as a whole unit, and to plug into the rational Bayes rules. All right, that's pretty much all the mathematical basis that we're going to use to derive, to create the probabilistic robot sensing and estimation. We're going to jump into example directly. So here is a robot, and this robot has a sensor which can sense if the door is open or not, is open or closed. We call this sensor measurement Z, and in the later of this lecture, everything related to sensor is denoted as Z. So here is like the sensor already tells you the door is perceived as open, but this sensor measurement is not the ground truth. It's not the truth of the state. What we want to know is like if the sensor tells you the door is perceived as open, what's the actual probability that the door is open? So here we have two different types of reasoning. The thing we are trying to calculate the probability of door is open given the sensor measurement is diagnostic, and the probability that the door is open and you actually the actual sensor measurement is still open is causal, and we call the second one as the sensor model. The thing about it is like the current state of the door is actually open, and you're trying to know what the sensor returns you. What's the probability that the sensor returns you the door is actually open? That's the sensor model. So compare those two different probability here. The sensor model, the causal reasoning is actually easier to obtain. If I ask you the question, it's like, how do you obtain the sensor model? In this case, you can simply just count the frequencies of your sensor when the door is actually open. You just leave the door open and use your sensor to read the measurement like 100 times. If 90 times that the sensor tells you the door is open, and then the PZ given open is 60%. And the similar examples could be applied to PZ given the door is actually not open, is actually closed, right? So the causal reasoning usually is a lot easier to obtain from the system, and the Bayes rule just to give us a great tool to how to use this causal knowledge to derive the diagnostic reasoning. Example here, for example, you are given the first two rows are the information you are given. You are given the probability that they given the door is open, which is 60%, and when you're also given that the probability that the P of Z given the door is closed is actually 30%. So if you think about that's actually, how do you think that? What do you think about this sensor model? Is this a good sensor or it's a bad sensor? If you think about when the door is actually open, and then the sensor, as there are 60% of chances, the sensor will tell you the door is actually open. It's actually a little bit over the average, right? So, and when the door is closed, the sensor tells you there is only 30% of chances that the sensor will tell you the door is open. So generally, this is a good sensor. It tells you some useful information compares to nothing, compares to no sensor, right? And also the prior knowledge, the prior probability about the state is just half and half because we have no other prior information about the system. So we just is a uniform distribution at this point. So, and then you plug into the Bayes rule we talked about in the last page, and then you can get the final result actually goes up from the 0.5. That means this sensor model raises the probability that the door is open. This sensor helps you to get a better information about the current state of the door. All right. If you have any questions, just bring it up anytime. And what about we have a second sensor? We think that one sensor is not robust enough, and we just installed another sensor to detect if the door is open or not. And we call this sensor measurement Z2, Z step 2. And more generally, if we have many sensors, we have n sensors from Z1 to Zn. How do we integrate those new sensor measurements to get a better information about the door state? So for the second measurement, first, again, you're going to be given the sensor model. The PZ2 given the door is open, and the PZ2 given the door is closed. So what about this sensor? If you think about this sensor, when the door is open, there is only 50% of chances the sensor tells you the door is open. And when the door is closed, there are actually 60% of chances that the sensor tells you it's open. So it's making the negative impact, right? Especially the second part, if the door is closed, but the sensor actually, there are 60% chances the sensor actually tells you the door is open. It's actually, if you just look at this sensor model, it's doing a negative job. And now the prior probability of the door is open is not 0.5 anymore because of the information we collected from the sensor 1. So the current prior probability goes up to two-thirds. And again, here we're going to integrate the second sensor measurement. We just use the Bayes rule with the additional background knowledge, or Bayes rule with the additional evidence, and we're going to take the prior probability P open given Z1 as a whole, and take the Z2 as additional evidence. And again, the formula here follows the Bayes rule. The only difference is just the regional state is not just P open, but it's P open given Z1, given the previous sensor measurement. We take that as a prior probability. And after calculation, you can see the probability of the P of the door is open actually goes down. The regional is 2/3. It's about like 67%, and now it goes to the 62.5%. So, and it actually matches our impression on the second sensor. As we talked about with this sensor model, the second sensor actually are doing having a negative impact on the overall estimation of the door state. So as we can see, based on the Bayes rule, it also tells you the door open, the probability of the door is open goes down. So Z2 lowers the probability that the door is open. This is a quite best answer. And everything we have talked about here, no matter with one sensor or two sensors, is all just about sensing. The robot hasn't put any actions into the environment yet. So the second part is about actions. And partially this word is dynamics because of the actions carried out by the robot, actions carried out by other agents, and also just the time goes by. All of those factors will change the word and make this word dynamic. So the problem is, how do we combine the actions into the sensing? Typical actions we have in the robotic systems is like if that's a mobile robot, the actions could be turns its wheel. If that's a robot arm, robot gripper, that could be the robot to grasp an object, and or if you have plants in environments, and then with the time going by, and then the plants grow, it also change the dynamics of the environment. So one thing we have to remember is like the actions never carried out with absolute certainty. It's just, let alone for robots, even for the humans, for such a sophisticated machine. If you think about the human body, all the actions we carried out are never certain. So if you think about, it's like a quick example here. It's like if you just close your eye and trying to lift your 2 arms and trying to touch the fingertip over your head, it's actually quite hard to get it at the first attempt. So that's the human dynamics, the human kinematic system, or the human's proprioceptive sensing is also has a huge amount of uncertainty when you're trying to execute certain actions. And those actions generally increases the uncertainty of the system in contrast to the measurement. And so how do we incorporate the actions, the outcomes of the actions into the belief of the or into the state estimation of the object in our system? So here again we formulate the action. First, all the actions in these systems are defined as U, and Z is the sensor measurement. U is the action, and we define the probability P of X given the current action and X prime. X prime is the robot state of the is the previous robot state, or the robot state at the previous time steps. So what we are trying to get is such a conditioning probability X given the action and given the previous robot states. And this probability could be interpreted as the executing U, how executing the action U will change the robot state from the X prime to the X, from the previous robot state to the current robot state. All right, and then continue the example we talked about in sensing, but now we are adding the actions into the system. And the action we are taking here is close the door. The U is close the door. And first we need to define the state transition, or you call it the action model in our system when we're doing the action of closing the door. And based on this state transition diagram, we can say if the door is open, the yellow node on the left, that's the state of the current robot state. If the door is open and you apply the action close the door, there are 90% of the chances the door is going to close, and there are 10% of the chances the door is still open. And if your current robot state is closed, and then when you apply the action close the door is still closed. It's always 100% the door is still closed. It's never going to be jump from closed to open with the action closing door. The method we used here to integrate the outcomes of actions is the total probability conditioned on the prior robot state X prime in both continuous or in either continuous or discrete case. The X prime here is somehow, if you just look at these equations as a pure total probability law, and the only thing we did here is introduce a new event X prime, and doing the total probability conditioned on this X prime. But the interesting thing is like the X prime is actually going to give us, we're going to introduce some interesting properties in a minute. But here, the only thing you need to remember is like we integrate the outcome to actions using the total probability by introducing the new event X prime. X prime is the prior robot states. All right, so once you are following the formula to integrate the outcome of the actions, everything becomes quite straightforward. We can first of all, and now we are still, because we're continuing in the last example, so the prior probability, the door is open is 5/8, and the door is closed is 3/8. That's a calculation from the example of the sensing. And then following the formulation to integrate the action outcomes, we only need to introduce a new event x prime, and because the x prime here is something we get from the last sensing example, and we can doing a total probability calculation conditioning on the x prime, the prior probability. So actually, in this case, I'm going to skip the detailed calculation here. If you're interested, you can check it out after class to see if your calculation matches the result on this page. The one thing you can probably notice that is like with the current action, the door, if the door has only two states, closed and open, those two are actually complementary. The summation is always 1. So once you got one result, you can just use the 1 minus to get another result. All right, we have talked about both examples about the sensing and the action and how we incorporate both sensing and action in the robot state estimation. And now we're going to create a rigorous framework about what is Bayes filter, and what's the input-output, and how do we create the mathematical formulations for the Bayes filter, and also how can we implement it with specific language. So the given input for the Bayes filter is first is the stream of the sensor measurement, we call it D, and also the stream of the actions, we call it U. So the D here is just a combination of the sensor measurement and the actions at the current time step, if we denote it as dt. Another thing we need to know is the sensor model. Sensor model is the P of Z given X is the sensor measurement given the current robot state, and the action model is the probability of the current robot state given the action U and the prior robot states. And lastly, we need an initial probability, or we call it like a prior probability of the robot state, P of X. And what we want is we want to estimate the state X of our dynamic system, or because we are doing this all in the probability theory framework, we basically want to calculate the posterior probability of the state, and we call it belief here, and which is defined as the probability of the robot state X given the data stream from the D1 to the DT. All right, hope this is clear. What's the input and what's the output of your Bayes filter? Before moving forward to create the algorithms, reading the given input and the output the posterior state, and we're going to revisit the Markov assumption. Markov assumption is assumption behind the assumption of the static word and also the independent noise. Independent noise here means your sensor noise and your action noise; those two are independent, which doesn't have a joint effect on your system, and also the model of your the sensor models and the action models are perfect without approximation. So there is a very strict assumption behind this Markov assumption. The Markov assumption itself tells you, could be visualized with a plot here. So originally, if we wanted to look into for example, if you look into a sensor model, you are trying to infer the probability of the sensor measurement at the time step t, and you need to consider everything before this node, everything before this arrow, and then take them into account. But now, because of the Markov assumption, we can only consider the arrow has a direct connect with this node. In this case, it's only the robot state at the time step t. Everything not directly connected with this node are ignored. And similarly, for the action model, the same is like we're trying to get the probability of the robot state at the current time step. Originally, we have to consider everything before this node, which is we're going to consider all the prior robot states, all the sensors, all the sensor measurements, and all the actions. But because of the Markov assumption, we are going to only consider the arrows connected with this node directly, and everything not directly connected can be ignored. Those can all be ignored. So in this way, we can simplify our sensor model and the action model into these two formats. In human language, now the sensor model is your sensor measurement. If you know the current robot state at the current time step, and your sensor model is only going to be conditioned on the current robot state. But the assumption is you have to know the current robot state. If you don't even know the current robot state, and then this Markov assumption doesn't stand. For the action model, when trying to infer the probability of the current robot state, and then you only need to consider the prior robot state, or the more accurately, you only need to consider the robot state at the last time step instead of all the prior robot states. You only need to do just one robot state before this time step, and also the action at the current time step. And this is the simplified sensor model and action model, and how you can interpret it with language. And if you think about this more, it's like for the action model here, the action model is, since we have translated into human language, is you're trying to estimate the current robot state with the previous state, with the state in the last time step, and your current action. So this is kind of like just a forward pass and trying to predict where the robot is going to be, where the robot state is going to be in the current time step. Somehow like open loop, you just ask a robot to move forward 10 meters or rotate 90 degrees, something like that. There is no constraint. And the sensor model is actually a step to set the constraint and set the correction. It's like you already landed on after you ask the robot to move forward for 10 meters, the robot is already moved 10 meters. The robot has already moved approximately 10 meters. It's never going to be exactly 10 meters. And then after the robot moved about 10 meters, and then you're going to use the sensor to collect the information and to correct the robot state if it's really about 10 meters or like 11 or 9 meters, something like that. So those two models actually work alternatively. It's like every time you apply your action model first, which is somehow like an open loop forward pass, and then you apply the sensor model to correct the errors you accumulated through the action. And then you do the action model again. You do a forward pass to command the robot to do the action, and then correct it with your sensor model. You do those two steps by turns and moving forward. All right, and that is about the explanation about the Bayes filter. And we're going to look into the specific mathematical derivations of those processes. And again, because of since I have talked about this, like we have two models here, and they are actually working in turns. The update process is also going to be separate. The one update is update based on the new sensor measurement, which is about the sensor model, and the one update is about the new actions. So every single time, because the original definition about the Bayes filter is like you have two data streams. One is the stream from the sensor measurement, and the one is the stream from the robot's actions. And those two streams, you collect the data separately, right? The sensor data is from sensor, and the action data is from the robot. And those two data streams are never going to come in at the same time. So we are also updating our robot state separately based on the type of the data, based on type of the input data. If the input data is the sensor measurement, we call this a perceptual or observation update. So the new data we have here is the sensor measurement at the current time step, say n. And we're trying to update the robot belief, to update the posterior probability of the robot state given the new sensor input. This is a definition of the perceptual or observation update. And everything here is just conditioned on the prior robot states and with the current new sensor measurement. All right, and this is the definition about the perceptual update when you get a new sensor input. So what can we do? Can someone tell me what we're doing in this step? Does it look familiar from this step to this step? All right, we're just simply doing, what we're doing here is simply doing a Bayes rule, Bayes formula, which we separate the new sensor measurement with the original robot states, with the original belief of the robot states, right? And if I circle out the new sensor measurement Zn here, you can see this is strictly a Bayes formula transformation. And what about this step? What we're doing in this step is, does anyone know what we're doing in this step, from the second to the third step? So what we're doing in this step is actually just applying the Markov assumption we have talked about in the last page. Based on the Markov assumption for the sensor model, the new sensor measurement, Zn, is actually independent to all the prior robot states if we know the current robot states. And this is exactly what we have in this item of the Bayes formula, right? So Zn is independent to all the prior robot, here is independent to all the previous d1 to dn minus 1 is all the prior robot actions and the robot sensor measurement if we know the current robot state, which is exactly the item here, the Zn given the x and the d1 to dn minus 1. So we can get rid of all the prior robot actions and the sensor measurement and just leave the Zn given x. And lastly, if we look at the denominator here has nothing to do with the robot state, right? So we can just pack this up as a normalization factor and plug into the equation. And what about this step? What we're doing in this step? Yeah, and we can notice that there is actually an item in the Bayes rule, which is exactly the definition of the posterior belief of robot state. Px given the prior robot states and the actions. Sorry, Px given the prior robot actions and the sense measurement. That's the definition of the posterior probability of the robot states. We call it belief. So in the end, we can simplify everything into this formula, which is we can update the current robot belief using the multiplication of the sensor model. This is the sensor model, and the times the prior robot belief. And this is just a part of the Bayes update. This is the update. This is the perceptual update based on the new sensor measurement. And of course, we have the other side. We have the action update. This is the update based on the new robot action. So what we have here is we are going to update the robot belief, update the posterior probability, given a new robot action UN. UN is the new action at the current time step. Definition of the action update. And can someone tell me what we're doing from here to here? Does this look familiar? Not at all. All right, this is we're doing total probability conditioning on the robot state on the last time step xn minus 1. If I circle out the xn minus 1, the robot state at the last time step, it should be quite obvious. This is strictly the formula of the total probability, but conditioned on a new event. We introduced a new event xn minus 1. And the xn minus 1 is the robot state at the last time step. Right? Yeah, total probability conditioned on the xn minus 1. All right, and after the total probability, what we're doing here? Markov assumption again, right? Based on the Markov assumption on the action model, so if we already know the current action and know the robot state as the last time step, xn minus 1, and then we can get rid of all the d from the d1 to dn minus 1. And we can simplify the first item into this form. All right, and lastly, here is a simple trick stuff we are applying is if you look at this item, the second item in the total probability, when you are calculating the probability of the last time of the robot state at the last time step, it's going to never be affected by the robot action at the current time step, right? The past history, the history is never going to be affected by your current actions. So we can simply just get rid of the robot action at the current time step in this item. This should be very intuitive. And lastly, again, this item is just the definition of the robot belief, which is but the only difference, this is the belief of the last time step, the belief at the step n minus 1. And the first item simply is the action model, right? So very straightforward. Any questions about those two updates? Perceptual update and action update. Those two updates are conducted alternatively. You conduct those two by turns. You do a perceptual update, and then you do an action update. And then you back to do a perceptual update, and then do an action update. All right. And then let's just put everything together. If you wanted to deploy this Bayes formula in any language you like, Python, MATLAB, C++, and then you will actually do those. You'll separate those two updates in your deployment as well, because in the reality, when you're having a robot, you have a sensor and the robot decoders on robot encoders on the robot actions. Those two informations will comes in different ways. So you do the update also in two separate blocks. Everything from here and based on from here to here is a perceptual update based on the new perceptual data Z, and everything from here to here is the action update based on the new robot action. The formula is just what we have derived from the last 2 pages. I'm gonna just to go through this pseudocodes block very quickly, which is how you actually implement your Python or C++ code when you are having those data streams, when you're having the action and the sensor data streams. Here is just a variant of the discrete Bayes filter. The only difference is when you are doing the total probability, you are doing the summation instead of the integral. Nothing new here. And lastly, if you are doing some derivation, this is not used for the implementation in the programming, but if you're doing some derivation, how do you combine those two updates together, combining the perceptual update and the action update together to get the final belief of the robot state? And this is how you do that. I'm going to skip the derivation here, and if you're interested, do that after class and check back to see if you get the similar result. This should be quite intuitive. I have noted every step, what we're doing at every step. For example, the first step, we are just doing the Bayes update, just doing a Bayes formula from the original definition of belief. And now the belief is the original definition of the belief, the P of xt, given all the actions and the sensor measurement from the initial and the current time step. On the left side, I have noted what we are doing at every step. For example, the first step is just the Bayes formula. Second step is doing the Markov assumption to get rid of the unused terms, unused variables in your formula, and similarly, total probability, Markov assumption, stuff like that. I encourage you to do that by yourself after the class and check back if you get the same result on your side. All right, let's do a quick recap of the Bayes filter. So for the Bayes filter, we have talked about there are 2 models here. One is sensor model, one is action model. And because of the Markov assumption, we can simplify those 2 models into a very neat format. Sensor model, the current measurement is only going to be conditioned on the current robot state. And for the action model, the current robot state is going to be only conditioned on the state of the previous step and the current robot action. So actually, but until this point, do you get any questions about how we're moving forward? What can we do with this Bayes filter, and what problems we may have if we wanted to deploy this on your robot? All right, so one question we have to face is like, how can we get this sensor model and the action model? How can we get this probability distribution, right? In the reality, you don't really know what's the P of Z given xt, and you don't really know what's the probability of xt given the xt minus 1 and ut. The actual distribution of those 2 probabilities are unknown. You have to think about a certain way to get either approximation or either get a get a model for those two probability distribution, right? Otherwise, there is no way to moving forward. And luckily, there are actually lots of different ways you can model those two models, model those two sensor model and action models, the probability distributions in these two models. So, and underneath the Bayes filter, we got a couple of extensions. And all those extensions is centered around this problem. How can we get the sensor model and the action model, right? You may heard about particle filter, Kalman filter, or histogram filters. Those are all well-known filters that you applied to do the robot sensing and estimation. But they are all originally from the Bayes filter. And the only difference is how you model your sensor model and action model, how you create those sensor model and action models in different ways. For example, for the Kalman filters, the core idea is you are trying to build these sensor and action models using the Gaussian distribution plus the linear transformation. And for the particle filters, is more like you create a set of the particles, which each particles are independently is a Bayes filter, which can do the transformation by itself, which is much more computationally heavy. If you just think about you're creating a set of particles, and each particle is a separate, is an individual Bayes filter, and to roll out this process. All right, and today we're going to mention a little bit about the Kalman filter, and a very important thing you have to remember is Kalman filter is just a special case of Bayes filter with a specific formulation of the sensor model and action model. And so everything holds in the Bayes filter, all the assumptions in Bayes filter, and everything, every derivations in Bayes filter still applies on the Kalman filter. The only difference is just the sensor model and the action model is how we create those two models in a specific way. All right, because the Kalman filter is just a special case of Bayes filter with linear Gaussian dynamics and the sensor model, so there are two components here. One is the linear transformation, and another one is the Gaussian distribution. Those are two core ideas. We're trying to create the sensor model and action model in the Bayes filter. Sorry, in the Kalman filter. So how do we do that? The original formula of the sensor model is P of zt given the xt, and now we are just creating a linear transformation, and we convert it to the zt is a linear transformation of the current robot states plus random noises. And for the action model, similarly, originally is xt given xt minus 1 and the current action ut. And now we are just doing a linear transformation. Again, we're doing a linear transformation of the xt minus 1 plus the linear transformation of the ut, which is the action, plus, again, the random noise. So this linear transformation it doesn't always reflect the real world, if you think about that. The current robot state is just a linear transformation of the previous robot state plus the robot action. Does it always true? It's not, but in most of the cases, it's close, could be close enough to approximate the real case. But you may have the question, it's like, previously this is a probability distribution, and now you convert it into a linear transformation. It looks like the uncertainty looks like it's gone, except you have the noise here. but the uncertainty is actually not gone. It still holds because of the Gaussian we are introducing here. We're introducing the Gaussian distribution for the robot states, and we start that with initial robot states belief of x now, and we model that as a Gaussian distribution. Initially, we model the initial state as a Gaussian distribution. And so, and you will say, because of initially the robot states as modeled as a Gaussian distribution, and this Gaussian distribution is going to be carried on in this future in the later steps. And we're going to talk about this in a second. But again, everything else is the same. The prediction and the correlation, this cycle, one prediction, one correction, back to prediction and the correction. This cycle is still holds in the common filter because everything is originally from base filter. All right, here it's just a detailed look at each component in the common filter. What's the matrix AT? What's the linear matrix AT, BT, CT, and the random noises represent? Gonna briefly talk about this. So the AT mainly represents how the states evolve from the last time step to the current time step, obviously, and the BT represents how the action changed the state from the t-1 to the last time step to the current one. And the CT is about the sensor measurement. It represents a mapping from your sensor measurement to the robot states, which we also assume that is a linear mapping. And lastly, those two random noises in the common filter represent the noises in the robot action and the noises in the robot measurement. And those two noises are independent, which has to fit the assumption of the base filter. And one more thing, it's like we modeled the initial robot state as a Gaussian distribution as well, with the mean is mu now and the covariance is sigma now. And we have talked about in the introducing slides of the common filter, we said it's like if the robot state is initially modeled as a Gaussian distribution, and then this Gaussian distribution, this Gaussian properties is going to be carried on in the future steps, right? Once we modeled the initial robot state as a Gaussian distribution, all the future states after the linear transformation is still a Gaussian distribution. Why is that? Because of the multivariate Gaussian properties. First of all, the first one is the linear transformation doesn't change its Gaussian properties. The only thing we are doing here is the linear transformation just to update the mean and the covariance of the new Gaussian distribution. So after linear transformation, the new variable is still a Gaussian distribution. And the second one is if you do the multiplication of two Gaussian distributions, the outcome is still a Gaussian distribution. It looks like this is not related to the definition of the common filter, but we're going to use that in a second. So basically, two things here. Linear transformation doesn't change the Gaussian distribution, and the multiplication of two Gaussian distributions still doesn't change the Gaussian properties. So once we started with a Gaussian distribution with a robot state, at the initial time step x now, once we started with the Gaussian distribution for this initial robot state, and then we're going to stay in this Gaussian world. We cannot, just using the linear transformation in the common filter, we're gonna never escape this Gaussian world. So everything we're doing afterwards are still contained in this Gaussian world. So again, similarly, since we have talked about common filter is just a special case of the Bayes filter, we're going to redo the derivation of the two updates. We'll redo the derivation for the action update and also the observation update. The only difference is we are kind of applying a new names for the action update and the perceptual update in the common filter because of some historical reasons in robotics. So now we are calling the action update dynamics, and we are calling the perceptual update or the observation update just the observations. Those like fitting more in those terminologies in robotics. But the first step of this common filter is we apply the initial belief on the robot state as a Gaussian distribution. We have talked about this multiple times. We started with the Gaussian distribution for the robot state. And then the dynamics, the action update. The action update, so now this is the new equations for the action update, changing from the, like, we add on to the original Bayes action update. And as we said previously, this is the original action update. This is the original action model in the Bayes filter. And now we introduced a new linear transformation in the common filter, and then we can directly plug in this linear transformation into the Gaussian distribution, which creates a new Gaussian distribution. Doesn't change its property, but just only with a new mean and covariance. And this one is the rational action model, right? This is the definition of the action model. P of xt given the ut and the x t minus 1. And now we are creating this model as a linear combination of the xt and ut. And because xt is originally modeled as a Gaussian distribution, and any linear transformation is not going to change these Gaussian distribution properties, only with the updated mean and the covariance. And this is more specifically, this is the updated mean of the new Gaussian distribution, and this is the new covariance of the new Gaussian distribution. All right, and if this is clear, if these two steps is clear, the core idea here is linear transformation for the action model, and because of the initial belief is a Gaussian distribution, we stay as a Gaussian distribution only with the updated mean and the covariance. So if these two steps are clear, everything after that is exactly the same as the original Bayes filter. I believe this should be quite familiar, right? Since we just talked about like 15 minutes ago. This is what we derived for the action update, in the Bayes filter. The only difference is now we have a specific form, a specific distribution for this action model, which is a Gaussian distribution. And of course, the belief of the robot state in the last time step is still a Gaussian distribution. That's just a replace of the time step. And all right, and everything here is what we got from the rational action update plus the new Gaussian distribution and the linear transformation in the common filter. And from here to here is simply just you plug in the numbers into the mathematical expression of the Gaussian distribution. And you will eventually get a quite long equation here. But don't scare, this is just you extend the Gaussian distribution mathematical formula. The only step here is there is a multiplication here. There is a multiplication between the action model and the belief of the previous robot state. That's why we mentioned, remember that? That's why we mentioned this Gaussian multiplication of the Gaussian distribution here. That's why we talk about this multiplication, because we're going to use it in the action update. And, again, this action update doesn't really change. It doesn't really change the Gaussian properties. And the only difference is we're going to create a new mean and the covariance in the Gaussian distribution. And here is the final expression of the action update in common filter. And you will notice that now we only need to update the mean and the covariance of the Gaussian distribution, and we can get rid of any other parameters here. This simplified our job a lot. We goes from those nonlinearity and all the complex in the systems into only two parameters in the Gaussian distribution with mean and covariance. All right, if this is clear, and then the observations, the perceptual update should be pretty much the same. The observations, as we defined in the common filter, this is going to be a linear function, the linear transformation of the state plus the sensor noises. With the original sensor model, the PZT given the XT, the original sensor model in the Bayes filter, we plug in the linear transformation and the Gaussian distribution of the robot states, we can get a new Gaussian distribution. And once we got the representation of the Gaussian representation for the sensor model, and then we can plug into the original, this is the original perceptual update in the Bayes filter. We just simply plug in the values we got in the common filter for the regional perceptual update. And everything after this is pretty much the same as the action update. You are doing a multiplication between the perceptual model and the old belief. So, which is actually a multiplication between two Gaussian distributions, which is still a Gaussian distribution. Plug into the mathematical expression, and you got the new mean and the covariance for your belief. Only difference is that the expression here is a little bit more complex, and we introduced a new parameter k to kind of to help with the expression in the final result. And the kt, which is regarded as an observation parameter, that we defining the mapping of the sensor to the robot states. And usually this kt is could be kind of fine-tuned in the actual application, which gives you the different mapping and give you the different state estimation in the final results. But in general, everything here is the same as the Bayes filter. We are only replacing the sensor model with the new defined linear transformation Gaussian distribution. All right, and this is how we derive the common filter, utilizing the linear transformation plus the Gaussian distribution on the robot states.
Could you give us some example for why it is reasonable to have that form for the sensor model in particular, why would the next observation be related to the state of the next observation just come from the environment?
Great. So you're asking it's like why this linear transformation holds in this assumption?
Why is it reasonable? Why are those Kalman assumptions reasonable? Why is it reasonable to, if you go back a couple slides,
Yeah.
to write...
Why is it reasonable to write in this form?
Why should ZT be related to XT? Usually what does C contain? Can you give us a little bit of intuition for those things?
Yeah, great questions. I'm about to talk about this in the next couple of slides. Yeah, the question comes back to is like why can we using those linear transformation to represent the sensor model and the action model, right? So in the reality, it's like most of the first. Let's think about probably you can look at this page, which is a breakdown of each component, each matrix in the common filter. The AT, BT, and the CT, which are the three most important matrices here. So AT, we're representing the state transformation from the last time step t-1 to the current time step t. And we are simply using a linear transformation since we believe most of the systems could be somehow break down into a linear system at a specific limited time steps. Even though it may be a linear system, but when you break down the time step into a small amount of time, it could be linearized into a linear system when you're transforming from the last time step to the current time step. In the longer term, of course, the nonlinearity is going to dominate. But if you break down into each small time step at the current time step t, this transformation usually could be represented as a linear transformation. That's about the AT. And the BT is a transformation caused by the action. Again, in the time small window, the impact from a robot action UT is also could be considered as a linear impact on the robot states. And lastly, the CT is about the sensor measurement. Sensor measurement is about the sensor measurement mapping to the robot states. It somehow depends on what kind of sensor you use. But for most of the sensor, like distance measure sensor or other type of sensors, I cannot name one right now. This linearity still holds in the sensor measurement mapping. When trying to map the sensor reading to the actual robot state, this linearity just intuitively holds in the sensor measurement because of the sensor decoding or stuff like that. That's why we are using linear transformation for the sensor model as well. All right. So generally, say, and those 4 slides are basically a brief derivation about the all key steps in the common filter, and in both updates, eventually we're going to becomes an update on the mean and the covariance in the Gaussian distribution in both action and the perceptual updates. All right, and again, the pseudocodes of the common filter, if you want to implement it, still there are 2 separate updates separated from here. Above is the prediction which is about the action update. Below it is a correction, which is about the perceptual update. And now you'll notice it's like everything we're going to updating is just centered around the mean and the covariance of the Gaussian distribution. And this simplifies the story a lot. All right, here's a quick recap of the common filter. Because of the linear transformation and the Gaussian distribution we utilized to represent the action and the sensor model, it is very computationally efficient. Linear transformation and could be run very fast in the most modern programming language. And also, if your system is a linear Gaussian system, which also exists in the very simple reality systems, and this solution is optimal. But as we said, does this linearity and the Gaussian distribution always hold in a robotics system? It's actually pretty rare. In the most of the case, both linearity and the Gaussian distribution do not really hold for a robotic system. The trick we're doing here, as I said, is like we shrink the time step into a very small amount of time, and then in this very small amount of time, we can regard the whole system as a linear transformation. But again, for the long-term non-linear system, common filter is approximation. The optimal here, the second point I said here, the optimal for the linear Gaussian system means the original system is the linear Gaussian system, and then this solution is optimal. And it could be run quite efficiently. All right, so what's the solution for other more complex cases? We're going to have extended common filter, which is how do we linearize a nonlinear system into linear systems effectively, and also unscented common filter, which is we're going to introduce the new concept of the sigmoid point, which is the separate point, which is a set of points we're trying to use to approximate the distribution of the sensor model and the action model. Everything is still centered around how do we model this, how do we formulate those sensor and action models in the Bayes filter. And then lastly, of course, if we are doing a data-driven way, we can have the learning-based common filters, etc. All right, before we finish today, we just want to bring up a quick example that I can think of that doesn't really work for the common filter, doesn't fit the assumption of the common filter. So if you have a robot and you are trying to, if this is a wall, and you have a mobile robot here, and you are trying to move forward move forward and get close as possible as close as possible to the wall, and then you have a sensor measurement, which can return you the distance from the obstacle to the current robot position, which tells you the sensor measurement. And this sensor measurement is going to, because this is let's say this is a time of flat sensor, so you measure the distance by sending a signal and then track it back, and then based on the time you spend in flight, then you can get the distance between the robot and the wall. And so if you think about the distribution of your sensor, it's all going to be centered around in this area. It's going to barely go to this area, right? So the distance measurement will something be like centered around this side, but it's never going to be on this side. This is a little bit weird. So it doesn't really, if you look at the sensor distribution, it's somehow probably going to be cut off at some specific point, which it doesn't really fit a perfect Gaussian distribution. So in that case, if your distribution of the actual measurement doesn't fit a Gaussian distribution, and then the common filter assumption just break down, and everything afterwards is going to be quite erroneous. Here is a simple example that common filter and the Gaussian distribution assumption in the common filter doesn't really hold. Of course, there are lots of other examples or other great examples that you may think of that cannot be handled by common filter, and that's why we are doing a bunch of extensions underneath the common filter category, including extended, unscented, and linear-based common filter. Or you may go back to the original problem that tries the different types of the base filters, particle filters, histogram filters, and a lot more. All right, that's pretty much all for today, and hope you learned something. And if you have any questions, just bring it up. Thank you.